at some more shortcuts, some derivative rules that make taking derivatives much, much easier. First of all, though, I want to take a look at kind of starting to look at how we use derivatives. We've done a little bit of this in the past. You might remember we talked about kinematics a little bit, right? About how velocity is the derivative of the position function and acceleration is the derivative of the velocity function. So we've touched on this a little bit. We're going to take a little deeper dive with that, and then hopefully we get to the product rule. That's kind of another big rule that we use a lot. Whenever you have a product of functions, you have to differentiate a product of functions. It's a little more complicated than just differentiating each function separately. We'll look at that today too. All right, so first of all, derivatives really are just rates of change. You always think of it as being a rate of change of one quantity with respect to another. So for example, dy dx is really the rate of change of y with respect to x, right? And that's really, isn't that what a slope means, right? What's the rise over the run? How much is the vertical component changing as the horizontal component changes? And that dictates what the slope of the tangent line is. F prime of x would be the rate of change of f of x with respect to x. That's how we'd write that. When the prime is there, we know this is the input variable, and so that's what we're differentiating with respect to. And then without the prime, that's the function that we're differentiating. Y prime is it's the rate of change of y with respect to, it doesn't tell us explicitly there, does it? It just says y prime. So presumably, though, we would know what y is written in terms of. What's the input or the independent variable there? And whatever it is, we're looking at the rate of change of y with respect to that. Okay, so then how would we read this derivative? If v of r represents volume as a function of radius, what is v prime of r, Lucy? What do you think?
Be the rate of change of the radius with respect to volume.
Other way around, right? It's the rate of change of the output with respect to the input always. Okay? So it'd be the rate of change of volume with respect to radius. Okay, so then if s of t represents position as a function of time, s prime of t is going to be what? What's that going to be, Cahill?
Can you repeat the question?
Yeah, so if just this middle one here. S of t represents position as a function of time. So s is position, t is time.
So change of position with respect to time.
There you go. We're going to change the position with respect to time. And if T of m represents average water temperature as a function of month, T prime of m would be, what's that going to be?
The rate of change of the water temperature with respect to the function.
With respect to
The month.
the month. There you go. Perfect. That's it. Very good. Okay. Good. This is where you see that, there are lots of applications of this in science. So for example, this is a real application here. R of V determines heart rate of a person whose heart pumps 5,400 milliliters of blood per minute and V milliliters of blood per beat. Okay, that gives us the heart rate, predicts the heart rate. Okay, and if you wanted to graph that, that's what it would look like. Okay. So, first of all, we're asked to find a rate here. We want to know what's the rate of change of the heart rate with respect to V, the output per beat. Okay, now think what that means. Think what that means here. For somebody whose heart is pumping 5,400 milliliters of blood per minute, that's not changing, right? That's staying the same. Okay, that's a constant. But the rate of change of the heart rate with respect to V. So if we nudge V, we're asking ourselves, what's going to be the impact on R, right? How is that going to change as V changes? If V is the blood per beat, right, the output per beat, this is what's predicting that. As the output per beat increases, the heart rate's gonna decrease a little bit, isn't it? If each beat is more efficient, then it takes fewer beats to push this 5,400 milliliters per minute, right? Okay, so there's one application. And it's easy for us to quantify this because we can take a derivative, right? We would just rewrite this from yesterday or from the day before yesterday. If we want to apply our power rule here, we just have to rewrite this as 5,400 times V to the minus 1, so the V looks like a power, right? And then we apply our power rule. So without looking, I guess maybe you can see that. What's the answer going to be? Okay, right? Because our rule is, remember, our power rule is we're going to multiply the exponent out front and then subtract 1 from the exponent, right? So we're going to get a negative 5,400 V to the negative 1 minus 1, so V to the negative 2. V to the negative 2 is just 1 over V squared, okay? So there's our rate. That's our derivative function that gives us our rate. And then we can use that to make some predictions. The heart rate at 60 milliliters per beat, well, all we got to do is feed that. That is just saying, so for part B, that's just saying R prime of 60, right? That's what is answering that question. Everybody see that? Okay. R prime of 60, well, feed it in there and see what you get. Turns out we get 90, I guess, right? Find the rate of change at V equals 60 milliliters per beat. Okay, so if we plug in 60, C is just going to be R prime of 60, and we get negative 1.5. Okay. Now, what would the units be? So the units end up being here beats per minute. Oh, sorry, I did that backwards. Whoops, this isn't R prime of 60, is it? Everybody agree? I read that wrong. This just part B. This just wants us to find heart rate at V equals 60. Well, that's what gives us heart rate right there. Okay? Everybody see that? So all we're doing is plugging 60 into the original function, R of V. So this is R of 60. And what would the units be? Okay, there's a little game you can play with the units here. If R, well, they tell us R is measured in beats, right? Beats per minute, okay? But when we take the derivative, how could we predict what the units are going to be, right? It's R prime of V. Think of it as writing that derivative as a quotient, right? R prime of V, oops. Equals, you fill in the blanks. It equals d what? D what? dr dv, right? Everybody see that? You always have the output on top and the input on the bottom. We would call this in calculus, a lot of times we'd call this the variable of differentiation. What are we differentiating with respect to? Okay, what's our independent variable? What's going to be on the horizontal axis? V in this case. So if you want to know what the units are, all you got to do is look at the units of the top. Well, what would the units of R be? Well, that's beats per minute, right? We already said that in part B. The units of R are beats per minute. What are the units of V? The units of V are milliliters. So we'd end up with an answer of beats per minute per milliliter. Does that make sense? Okay, so it's easy to predict what the units are going to be if you just think of the derivative as a fraction or quotient. Units of the top, the top quantity divided by units of the bottom quantity. Okay, give me 1 to 5 on that. That's how we do it. Okay, based on data from a research group, a model for the total stopping distance of a moving car in terms of its speed is this. They're giving us a function here. S equals 1.4 V plus 0.054 V squared, where S is measured in feet and V in miles per hour. So they're telling us that, right? That's what's our input and what's our output for this function? What's our input? V, okay, so output is S. Really what we probably should do with that, is there a better way to write that? How should we probably write that? Instead of S, we should probably write that as S of V. Yeah, everybody see that? We want to, and might as well take advantage of the fact that we can write this as a function, which tells us every time, what's the input, and it allows us to use, when we use that function notation, we can evaluate, I could like calculate S of 10 or something, or S of 3, or whatever my input is, okay? So we want to probably always rewrite that as S of V equals 1.4 V plus 0.054 V squared, okay? The linear term 1.4 V models the distance the car travels during the time the driver perceives the need to stop until the brakes are applied, and the quadratic term models the additional braking distance once they are applied. Okay, good enough. Nice to know. Find ds dv at V equals 55 and V equals 75 and interpret the meaning. Well, let's first just calculate let's first calculate what is S of 55. Somebody throw that in your graphing calculator for me real quick. Or I'll tell you what, I'll remind you about how to use Desmos for this. Right? You can either use graphing, it doesn't matter which one you have. It's either graphing or scientific. You can do the same thing in either one. I've got the scientific here. Remember how to do this. All I've got to do is define the function. So S of V equals 1.4 V plus 0.054 V. Whoops. What did I do there? I don't know how I did that. V squared. Go down to the next line, and we'll evaluate that. So I get S of 55 is what I'm looking for here. And that, whoops, darn it, where'd that go? And that first one. S of 55. So I get 240.35, roughly. To 2 decimal places. Okay, what should the units be? Feet. Great. What's that telling you? Okay, everybody agree? Pretty straightforward, right? At a speed of 55 miles per hour, the predicted stopping distance is a little over 240 feet. Okay? And we can do the same thing for V equals 75, right? Let's just do that real quick. So if we do S of 75, and this is super handy in Desmos to take advantage of this. All I got to do is go back here and change that to 75, and I get 408.75. Okay, well, first of all, does that seem linear to you? I mean, an increase of 55 to 75, that's an increase of less than 50%, right? Look at this increase in the stopping distance. It almost doubles, right? So as a physics guy, used to always talk to my physics classes about this. And a parent, I cannot impress upon you enough how dangerous cars are. Cars plus speed equals danger. because these are the kinds of things that people, so I'm gonna take a pause from the math for a second here. You gotta allow me to do this as a dad. People are not built to see things non-linearly, right? If you think about the speeds at which we've evolved to do things like hunt and run, they're pretty slow. And so our brains generally think about things in terms of linear relationships. That's just, it's easy to do, and that's what we do. But when you start to move at higher speeds like this, you get these non-linear impacts become really significant. And so look what happens to the stopping distance. Think what happens to the energy. Like, I don't know if you guys have talked, who's in physics? You guys talked about energy yet? Kinetic energy. Okay, so kinetic energy is proportional to speed squared, right? And when you crash in a car, really what you're having to do is dissipate all that energy, right? And so if you double your speed, you're quadrupling your energy. And so it's the energy that the car is having to give up in the collision is really what's causing, that's really the dangerous part of it. And that's increasing quadratically, not linearly. So it may not seem like much, but increasing your speed from, like 70 to 80, on the freeway, may not seem like a big deal. By percentage, it's not very much. But in terms of stopping distance, in terms of the energy you're giving up in a collision, it's a huge deal. It makes a really big difference. And if you think, here's the other part. If you think about, like, we're just a kind of a sack of important organs and things, right? And it's anything below a certain threshold impact force, right? Or pressure, if there's sharp parts of the car you're going to impact. Anything below that threshold is survivable. It's not like there's some gray intermediate area in between. Either you're going to survive or you're going to die. And all it takes is to just pass through that threshold, and it makes a big difference, right? Living or dying. And oftentimes, because of these nonlinear relationships, people don't really understand what a big difference, how much bigger risk you're taking if you're going faster. So just don't drive fast. Don't drive fast. It's not a good thing. All right, I'll get off my dad chair up here and we'll get back to some math. So we understand what these things mean, but what about rates of change? So ds dv, that's the rate of change of speed with respect to, or stopping distance with respect to speed, right? S is stopping distance, v is velocity or speed. Okay, we could take this derivative. That's an easy, let's do it real quick. What is the derivative? Good practice for us. What is that derivative, Shay? What are we going to get for S prime of v? So here's the function we're differentiating.
Is it 1.4?
Good.
And then plus.
What is that going to be? Well, it's 2 times that, right?
Yeah.
So 0.108. B, there you go. Good. Okay. So there's our derivative function. That's the rate of change of stopping distance with respect to speed. Well, let's see what happens here. Let's look at these two. What's that telling us? That's harder to appreciate what the meaning of that derivative is.
How many people did they increase from 1
Okay, so it's a good way to kind of think about it is, if I were to increase my speed by 1 mile per hour, how many additional feet would I add to the stopping distance? Okay, did everybody see that? Is that technically true? Not really. It's not really true, because if I increase my speed by 1 mile per hour, the function has changed, right? And so it's really not, you're not, it's not like you're actually, this would be less than what I'd actually find. If I changed my speed by 1 mile per hour, my stopping distance would increase by slightly more than that, okay? So although that's very close to the idea, and it's a good way to kind of get a baseline understanding of what that means, what it's really telling me here is, and listen very closely to this, because this is kind of this is language that you're going to hear again and again in later math classes. How sensitive is the output stopping distance with respect to changes in the input. And that number by itself may not even be super useful, but it is useful to make a comparison between those two, right? What do we notice here? We notice that when the speed is higher, the stopping distance, changes in stopping distance, or stopping distance is more sensitive to increases in speed when the speed is higher, right? So if I'm traveling at a faster speed, any slight increase in speed is going to be even more dangerous than it was at a lower speed. Does that make sense? The function is changing more rapidly. The stopping distance function is increasing more rapidly as speed changes at 75 than it is at 55. That's a tough one to, and the more calculus you do, the more you'll kind of get a feel for that. I'm curious, just give me like a 1 to 5 on that one. I just want to kind of know where, that's a tough one. Okay? Just curious where people are on that concept. How do you get at the meaning of the derivative? Okay? So here's what they say down here, and I kind of disagree with this a little bit. I mean, this is close. The derivative represents the additional number of feet needed to stop a car for a 1 mile per hour increase in the speed. Kind of, not really. Not really, because the function may not change linearly over that 1 mile per hour, right? But it's a good way to kind of think about it. More importantly, though, it's a basis of comparison. Okay, here's another really good way to think about this. This will help, I think. So you've all been in this situation probably at some point, right? When you're blowing up a balloon. Raise your hand if you've blown up a balloon before. Everybody's blown up a balloon. You can all relate to this. At first, it's pretty satisfying because every deep breath you take, you're getting big increases in the apparent size of the balloon, right? But what happens after a while when you're blowing up a balloon? Each big breath you're puffing into the balloon, you're hardly seeing, when it gets fairly big, you don't even see any change in the balloon anymore, right? You're not seeing much of a change. How come? Well, because of the relationship between volume and radius, right? Volume changes non-linearly with respect to radius. Everybody see that? So initially, increases in volume give you pretty significant increases in radius, but after a while, when the balloon gets pretty big, think about that additional, if you take the volume of that additional breath and you spread it out, imagine it's going to be a thin layer that you're adding to the volume of the balloon. The bigger the balloon is, the thinner that extra volume of air you're pushing into the balloon is on the outside of the balloon. Everybody agree? When we start off, when the balloon has a really small radius, an extra input of volume is going to change that radius by quite a bit. Okay? So let's take a look at this with calculus. If we calculate the rate of change on this one, what is V prime of R? What do you think? Gabe, what's V prime of R there? There you go, right? 4 pi r squared. Take the 3 down times the constant, and 4/3 pi, that's the constant, isn't it? Pi is just a constant. So I get 4 pi r squared. Okay, so then, what happens if we have a radius of, let's just say 1 centimeter compared to a radius of 10 centimeters? V prime of R, V prime of 1 is equal to 4 pi, right? V prime of 10 equals 400 pi, right? So what's that telling us then? The rate at which the volume is changing as we increase the radius is much bigger for 10, right? It's a tremendous increase in volume to get a slight increase in radius when the radius is big compared to when the radius is small, right? Increases in radius here give us small increases in volume. Okay? Everybody see that? Okay, so on to the next topic, derivative rules. So I'm just gonna give you some. Because we're doing this day on, day off thing, I mean, I love to prove these things because you get to, and I think it's good for you guys to see some proofs, but I just don't feel like we have time for that. I'll save that for when you're in college. We'll run you through all kinds of proofs. I just want to be more applications of calculus and just practicing, doing calculus this year in the limited time that we have. So I'm going to resist that temptation and just give these to you, and we're going to learn how to use them well. So here are some derivative rules. I'll tell you what, I'll give you a paper handout that's got these and more. And we'll just kind of add to this short list here for a while. And I'll put these on Plan Book and on your Google Classroom. I'll add these. This is a handout. And every time we add more derivatives, I can change the handout. Okay. The derivative of a constant, we've already talked about, is 0, right? The derivative of a sum or difference is easy to do because you just differentiate term by term. You just differentiate each term separately. We know this is a big one, right? We know the generalized power rule. The derivative of a constant times x to the n is the constant times n x to the n minus 1. You guys are great at that. We've already worked on that. You've shown me today, you remember that one. The derivative of sine x is equal to cosine x. The derivative of cosine x is equal to negative sine x. Don't miss that negative sign. And I'm going to give you one more. And again, I'm not going to prove this one, even though it's killing me not to prove this. The derivative with respect to x of e to the x is e to the x. That's a weird one. Think what that means. Pretty bizarre. If we look at the e to the x function, that's just the 0.01. That's our exponential curve, right? That's telling us that at any value of x, the slope of the tangent line is always equal to the value of the function. How about that? If you really think about that, that's kind of a weird relationship. The slope always equals the value. Okay. In a way, that's almost the best definition of an exponential function. It's a way you could define an exponential function as the locus of points for which that relationship is always true. Okay. It's not how we do it, but it would work. Okay, so let's practice these a little bit, see if you can remember. So how about part A? F of x is 3e to the x. What is f prime of x going to be? 3e to the x, right? How come the 3? Well, because the 3 is a constant. So the 3, we just pull that out in front of the derivative. And really what this is the same thing, by the way, as saying, in fact, I'm going to write this a little different. I'm going to pre-write this. This is the same thing as saying 3 times the derivative with respect to x of e to the x. The 3 we can just pull out in front of the entire derivative and differentiate the function part, and then distribute the 3 when we're done. Okay, which gives us 3 e to the x. Okay, what about part B? Nora, what are we going to get for part B here? It's a sum, so I can just differentiate term by term, right? I can just deal with each one of these separately. So what's the derivative of x squared? Say it again. 2x, good. And then derivative of e to the x? There you go. 2x plus e to the x. Okay. How about the bottom one? Let's see. Ashton.
Cosine x minus x.
There you go. Okay. Now, that seemed pretty simple, but think what we just did. I mean, that's pretty cool. We came up with rates of change of all 3 of these fairly complicated looking functions pretty easily once we get those derivative rules. We don't have to mess with all those limits anymore, right? We've got a growing list of rules where we can just sidestep all that extra work. Okay, so what about, when are we out of here? We got like 20, 25, okay, good. So I think we're at least going to get this set up. So how could we do the top derivative then? let you think about that for a second. Does anybody have any ideas? Does anybody see a problem with that? How would you describe h of x in that top function? Is it a, like in terms, is it a sum, a difference, a quotient, a product? What is it? If you kind of look at this from the outside in, it's a product, isn't it? Everybody agree it's a product of two factors? Remember, factors in math are things that are multiplied, and terms are things that are added or subtracted, right? So it's a product of two factors. We've got the green factor and the yellow factor, or gold factor, green and gold, what am I saying? The green factor and the gold factor. Okay, but what's missing from our list of rules? Well, we don't have a rule for products, okay? So as much as it might seem like this is going to be an easy one, we don't know how to differentiate this yet as a product, okay? But could we change this to a function that we could differentiate? What would we do? Distribute, right? If we just kind of FOIL this out, what do we get? Well, if we FOIL this out, I'm going to get 3x times 5 is 15x. 3x times 4x is plus 12x squared. Negative 2x times 5 is negative 10x squared. And negative 2x squared times 4x is negative 8x cubed. So I could rewrite h of x as 15x if I combine like terms plus 2x squared minus 8x cubed. And now that's easy to differentiate, right? Now we wrote that as a polynomial. And differentiating a polynomial means I'm just differentiating each term separately using the power rule, right? So what are we going to get here for Julia for h prime?
15 plus 2x.
Plus what?
2x. Oh, 4x.
4x?
Minus 24x squared.
Good. Okay. Everybody give me thumbs on that. We good? Okay. All right. What about this bottom one? Can we finesse our way out of that one? No. Right? There's no way to rewrite that as anything other than a product. It's a product, so we're stuck with it. So we need a new rule for that then. We need a rule for how to differentiate products. So rather than make this, I can't resist to at least like showing you the proof, even if we don't go through it all the way, writing out each step laboriously and talking about, we'll at least take a look at it, because this is kind of an interesting thing you can do here. We're trying to come up with the derivative, so we're going to start off with the limit, right? If we want to come up with a proof for a derivative rule, we have to go back to fundamental principles and start with the limit, deal with the limit definition of the derivative, and then if our outcome can be generalized, we won't have to do it anymore, right? So we're going to keep this completely general. We're not going to specify what f of x or g of x are. And because it's completely general, our result should be completely general also, right? So h prime of x, by our definition, because this is an h, I'm going to use delta x's instead of h's, right? So h prime of x would be h of x plus delta x minus h of x over delta x as delta x goes to 0. That probably looks real familiar, right? Okay, well, what is h of x plus delta x? If h of x is f of x times g of x, then h of x plus delta x would be f of x plus delta x, g of x plus delta x, right? Okay, well, what is h of x? H of x is just minus f of x times g of x. Okay, this is one of the very few times in math. This one, we almost never use this approach where we're adding 0. All the time we multiply by 1. We multiply the top and the bottom of a fraction by something to help us out, right? To change, to rewrite in an advantageous way what we have in the top or the bottom. But almost never do we do something like this where we're going to add 0. Well, in this case, we're adding 0 in the form of We're adding f of x plus delta x times g of x, and then we're subtracting the same thing. Why would we do that? Well, we're going to do that so we can regroup this in a way where factoring helps us. Okay? I just want you to see a proof like this because you'll see something like this again in the future. And having seen it once, it'll help you to follow it in the future. So what can we do then? If we group this in such a way that we're going to group the first two terms in the top together and the second two terms together, and we'll just split those into separate fractions. Okay? This first term over here, the first term, I could factor out of the green grouping. I could factor out an f of x plus delta x, right? Everybody see that? If I factor that out of each term, I'm left with a g of x plus delta x minus g of x. And I've got a delta x is in my denominator, the whole thing. I have a common denominator. But because I've got a product of this factor times this factor, I'm going to group the delta x with whichever one I want, which is the second one. How come? What does that look like? What's the limit of g of x plus delta x minus g of x over delta x as delta x approaches 0? What is that? That's just g prime of x, right? How about the other grouping over here? Well, in my purple grouping, I could factor out a g of x, leaving me with f of x plus delta x minus f of x. Well, what's that look like in my limit? If I send the denominator over to my second factor over here, that looks like f prime of x, doesn't it? Right? And so what this is already looking better. I've got the limit of f of x plus delta x times g prime of x plus g of x times f prime of x. But in my limit that delta x goes to 0, would everybody agree that f of x plus delta x is just going to go to f of x? Right? And look what we end up with there. The result, if h of x is the product of f of x and g of x, h prime of x is f of x times the derivative of g of x plus g of x times the derivative of f of x. And there's our product rule. Okay? So there's a kind of a cleaner writing of our power rule. The derivative of a product is equal to, we'll just call this first function, second function. Derivative of a product of two functions is first function times derivative of the second plus second times derivative of the first. Because they're added and addition is commutative, it doesn't matter which one I do first, right? I could commute these two terms, exchange places, and it wouldn't change the outcome, right? Very easy rule to apply. It's a little bit easier to see. A lot of times, this looks kind of, that's just hurts to look at that, doesn't it? There's so many parentheses and x's and f's, and it just looks complicated. So a lot of times when we're dealing with products and quotients of functions, we'll just say, okay, rather than calling it f of x and g of x, let's just let u equal the first function and v equal the second function. So then the derivative with respect to x of u times v is just u v prime plus v u prime. Okay? It's a cleaner, easier way to write the derivative. We could extend this product rule if we had a product of 3 instead of 2. Look what happens here. You follow the same pattern. I'm going to get, if I have the product of u times v times w, I'm going to get the product of u times v times w prime plus the product of u times w times v prime plus the product of v times w times u prime. So each term gets its own term having the derivative in it, right? It's always a product of the three functions, and each time one of them is a derivative and the other two are not. If I had 4, what would happen? Same pattern, right? We just would have 4 terms instead of 3. Okay, we out of here in 1 minute? Okay, that's a good place to stop. We'll practice that a little bit next time, and I'll add the quotient rule. I'll put the assignment up, but you may not be able to do the whole thing yet until we meet next time. You can get a good run at it, though. Get a good start on it. How we doing on this stuff? Give me a little feedback here. Is it good? Okay. Power rule assignment going okay? Okay. Anybody need me to request them? Good.